What's up, guys? Welcome to our technical session. My name is Stillman Tate.
I'm Zach Giannini. I'm Chris Giannini.
I'm Kyle Vibberman.
And we're all from Cambridge High School in Milton, Georgia.
In this technical session, we'll be going over the design and build process of our Electrathon vehicle, as well as a brief overview of what Electrathon vehicles are. Okay, guys, so first we'll start off with a brief overview of what the Electrathon spec series actually is. So Electrathon USA is the sanctioning body of this race. It's essentially like any other race series you see on like TV, like NASCAR, F1. The sanctioning body happens to be Electrathon USA, and so in the Electrathon race, what you do is you design and build a car, or you can buy a kit if you want. And it's an hour-long endurance race with electric vehicles. So they're all electric vehicles. There's two classes. You have the lead-acid class, which is the normal like big class that most people race in, and and then there's also the advanced battery class. So and then actually at Georgia TSA they have a Electrathon Rally, which uses the exact same rules, except we just aren't sanctioned by Electrathon USA. But it's essentially an event in the exact same format and to their rules, so we use the exact same cars. And so the car we're building, actually, we do plan on racing, as well as in TSA State and Fall Leadership, we plan on racing in actual Electrathon car races. These Electrathon vehicles are powered primarily by lead-acid batteries in the main class, which is pretty much the only limiting constraint other than the safety concerns they have, like stuff like roll bars, seat belts, overall car like length restrictions, and then other than that, really the big power limiting factor though is the 73-pound lead-acid battery cap, and as well as your driver has to weigh a minimum of 180 pounds. And then there's also the advanced battery class where they used alternative battery types, where you, depending on the battery type, it will, for instance, a lithium ion, you just have a max weight of 14 pounds instead of 73 for lead acid, and as well as a 1 kilowatt hour max battery output pack.
So yeah, over the past 7 months, we have been designing and developing our new iteration of that. It is the lead-acid base that's going to be racing in that class, and we are taking all these regulations into account and designing what we hope to be the best and fastest car there.
In the past, we started out racing last year in the actual class. The car we're building this year is the third car our program is built. The first year was my freshman year, and we built the car. We really didn't know what we were doing, so we just built the car, got it running. And we just we didn't actually race in any real races from that. We took what we learned from that, built the next car, which we raced last year at Fall Leadership and State. And Fall Leadership was our first ever race, so we really didn't do too hot in that. We took what we learned from that, made some changes, and then at State Leadership, we took fifth in our heat and CAT. We are now, after a couple months of R&D and CAD, we have the sixth version of that third physical car. So we are now starting to build the sixth version that we've designed since State Leadership Conference, and that will be our third physical car that we hope to dominate the rest of our competition with.
Yeah, so a lot of work's gone into this, and over the next couple of minutes, we're going to talk about all the design we've put into it, what each component is. All of us will be talking over specific sections, so you guys get to learn about it and what we're doing this year. The four major topics we're going to be hitting on is chassis, drivetrain, like electronics, motor, batteries. And one big thing we learned from last year's car was that it skidded a lot in the corners, so we decided to add suspension this year. So we're going to be talking about that. And lastly, aerodynamics. We're going to hit on that real quick too.
And now I'm just going to go straight into the frame design.
So this is a SOLIDWORKS frame file for our program's third Electrathon vehicle. This is a sixth iteration of our frame design for this car. And obviously a lot of different things have changed over the previous years. In this video segment, I'm going to get into some design factors and elements of our frame, as well as some things that have not only changed throughout the previous years, but have also changed throughout the design process of this car as well. Now, when we first started to design this vehicle, we thought that the frame was going to be made out of aluminum. Due to some fabrication difficulties and safety concerns, we had to switch back to box tube steel. Now, to cope with this weight gain, we thinned the gauge of our steel, as well as added things like flat bar in places where box tube steel would not be needed. Things like places where only bodywork is supported, like this back here, or this front right up here at the top, or places like where we're majoritively supporting things like battery trays, right? Like right here and right here. Okay, I'm going to get into the seating position of our driver, as well as the exterior appearance of our car. Okay, so the seating position of this car is somewhat like an F1 driver seating position. When you sit into the car, your entire body is submerged into the frame, excluding your head. This not only improves our safety odds, but also extremely lowers our center of gravity, improving our handling, and lowers our car. This means that our drag coefficient is improved. Now, how we've been able to do this is we built our seat into our frame itself. Unlike other teams who mostly have a seat into a frame, we are able to sit lower, and we're able to make the seat a structural part of our frame. Now, speaking of center of gravity, with everything in it, our center of gravity is expected to be right in the middle here on the bottom half of the car. This is exactly where we want it because it dramatically improves our handling, as well as evenly distributes weight across all 4 tires. Now, our frame has already shown to be extremely strong, as it has been positioned between 2 tables, and one of my colleagues have already bounced on it with no flex at all. Okay, I will let my colleagues get into the aerodynamics and suspension aspects of this car as well.
So before we talk about the suspension on our car, we're going to do a quick overview on suspension geometry. And there's going to be 6 parts of suspension geometry that we're going to talk about. So the first one is toe. So toe is how far in and out your tires towards the car. We have it drawn right up here. So toe in up top is if your tire is angled in towards the car, and toe out right down here is if it's angled out from the car. And this is the front right up there, yeah. And beneath it we have caster. So caster is this is positive caster right here. These are the ball joints on your suspension. So when we show you our suspension, there's these 2 ball joints up on the wheel upright, and the position of these creates what's caster. So if the top one is further back towards your car, and then the bottom one is close to the front, that creates a positive caster. And then the exact opposite is underneath. That's a negative caster. So that's if your top one is closer to the front of the car, and your bottom one's closer to the rear of the car. So what caster does is it's like wheels on a shopping cart. Positive caster makes sure your tires stay going forwards, and negative caster nobody wants just because it doesn't do anything good. And then our next aspect is camber. So camber is how far in and out your tires are tilted towards the car. So there's the top of our car, here's the bottom. If the tire is tilted in towards the car, that's negative camber. A lot of cars want that because it keeps the car from tipping over. And then you can see here on the opposite side we have positive camber. And positive camber is the exact opposite if the bottom of the tire is facing in towards the car and the top of the tire is further away from the car. That affects how you handle and make sure your car doesn't tip over. The next thing I'm going to talk about is KPI. KPI stands for kingpin inclination, and what that is determined by is, again, these 2 ball joints right here. Except for this time it's from the front view. So here's the top of our car right there, and here's our 2 tires. So the ball joints coming off the suspension on the uprights create an angle right there. Now that angle is called the kingpin inclination. And what that determines is a scrub radius. Now a scrub radius is, what that affects is how much your car is heavy or how light the steering is, but also how much feedback you get from the road. So the scrub radius is determined by where the point of the kingpin inclination meets the ground, and the point of your contact patch. That creates a scrub radius. And on this instance right here, we have a positive scrub, meaning that the kingpin inclination is in closer towards the car than the contact patch, the center of the contact patch. And what that is it gives you heavier steering. However, you also have more feedback from the road, meaning that you can tell on how the tires are going to behave. The exact opposite is seen over here. That's a negative scrub radius. Your steering is a lot lighter than this, but you don't get as much feedback from the road. Now Zach's going to go over and talk about the other 2 aspects of suspension geometry.
So the other 2 aspects of our suspension we're going to be talking about is anti-roll and anti-squat geometry. So these are essentially the points where the car pivots about when it's stopping, accelerating, and moving left to right. So let's talk about anti-squat first. To determine your position, which your body squats about, you have to draw a line between these top 2 attachment points where the control arm is attached to, draw that out, and then draw the bottom two, and where those meet, you draw a line to the contact patch. That's one side. Do the same thing on the other side. Now these two lines right here, where those intersect, that determines where your squat is. So the advantages of this is we can, when we're launching off the line, or when we're launching out of a corner, we're making sure our body doesn't rotate back too much. And same thing when we're stopping, we're making sure our body doesn't rotate too far forwards. The advantage of this is the closer you get it towards your center of mass, the better off it is. Now down here is our anti-roll geometry, and so this is basically the body tilt from left to right. This is how to help negate it. So what you do for these is you draw a line between your top control arm to a point, your bottom control arm to a point, and then from that point you draw to the contact patch. You do the same thing on the other side. And again, this determines the point to which your car rotates about. Now, if you move it slower to the ground, it means your body's going to be rotating more and more. If you move it higher up, it means your car is going to be rotating less and less. The advantage of this is you can determine lift, you can determine roll, so it's a balancing act. We chose to have ours about 3/4 of an inch below the car, and so that's what we've determined has been a good point right now. And then this is how we're going to help negate body roll and body squat.
So now that you know a basic suspension geometry, I'm going to talk about how we incorporated suspension geometry when designing our car and how our car suspension works. So I'm going to go over the front suspension, and while Zach can go over the rear. And in the front, we have what's called a rocker arm push rod, or sometimes just referred to as push rod. Now, this is the setup that most modern Formula 1 cars use. And it's broken up into 3 components: your inboard suspension, your outboard suspension, and then everything in between, or your wishbones and your push rod. So I'm going to start with the outboard suspension. So the first thing is your wheel hub right here. This is made out of 3/8 steel and has these 2 tabs coming off it right here. Now, as you can notice, there are these ball joints coming off it. And those are the exact same ball joints I was talking about when talking about our KPI and our caster. Now, right here you can see our KPI is drawn right there between those 2 ball joints, and our caster right here drawn between these 2 ball joints. Now, what we didn't talk about is our inboard suspension, and this is where things start to get a little bit more complicated. So whenever your wheel moves up, it moves this push rod in towards the frame, which rotates our rockers, these 2 plates here, around the torsion bar, which is this bar, our rod right there. Now what that does is it compresses the shock absorber right here, provides resistance, just like how it would be in a double wishbone. Now, a double wishbone is a little bit simpler than this. You will replace the push rod right there with your shock absorber. Now, the reason we didn't do this is because your shock absorber is out in the airflow, and your center of gravity is not, your mass isn't as close to your center, meaning your handling is not as good. And what this also allows us to do is to do an anti-roll bar. So an anti-roll bar is what these 2 bars are here, dropping down to this bar, which is our anti-roll bar. And what it does is it links one side to the other. So whenever this side moves up, the other side moves up with it. So what that allows for is for the body to not roll as much, and therefore being an anti-roll bar. Now, the final thing to talk about is what's everything in the middle, our wishbones and our push rod. So these are on the airflow, so they need to be as small but as strong and as aerodynamic as possible. So we are planning on carbon fiber wrapping these and making them teardrop shaped to be as smooth as possible in the air. And how these are connected are through these spherical rod ends right here to these plates, which attach back to the ball joints. Now, one thing we didn't mention is how you control toe. If you remember toe, that's the first thing I talked about. So in the front is controlled using these tie rods, and however long or short your tie rod is determines how much toe in, how much toe out you have. The longer your tie rod, the more toe in you have. The shorter your tie rod, the more toe out you have. Now, one thing we didn't talk about at all is bump steer. And bump steer is how your toe adjusts as the suspension moves up and down. So the way that's controlled is through the positioning of your steering rack. So where this is right here. So the more up you move it, the more toe in you have in bump steer, and the more down you move it, the more toe out you have. So we have it adjusted so we have 0.02 degrees of bump steer, which is minimal. And that allows for us to keep our guard going nice and straight and make sure that we handle just as smooth as we should. So here's our rear suspension. It's very similar to the front, but slightly different. Instead of going with the typical double wishbone style setup in terms of the control arms, we went with the multi-link suspension. Now there is one major advantage to this, and this is that you can create a virtual pivot point. Essentially, the point of which the axis of which the upright pivots upon. The advantage of this is you can create your KPI in a very advanced way while minimizing the amount you have in your actual control arms. So we can essentially move our virtual pivot point all the way out to here instead of in here, yet keeping our actual wheelbase narrower than we want. The advantage of this is, of course, we can create a KPI that determines our scrub radius a lot easier than using a typical double wishbone setup. Now, the transfer of the actual suspension works in the same way as the front. We have a push rod attaching up to a rocker back here that rotates along a torsion bar and then goes down, of course, to our shock absorber. That's basically it for the rear suspension. We don't have a lot of an anti-roll bar because we didn't have space for it due to the differential right here. In addition, though, we do have these two U-joints along the rear axle to make sure it can pivot up and down with the control arms. An important thing to account for when designing our car is aerodynamics. Now, there's two major things in aerodynamics we need to focus on: downforce and drag. Now, let's talk about what downforce is. Downforce is essentially negative lift. And the advantage of downforce is you get higher cornering speeds due to grip. Downforce is when you're pushing down on the car and your tires push from the ground more, giving you more grip. Now, this is helpful for us in Electrathon because the faster we can go through the corner means we don't have to accelerate as much, meaning we don't have to draw as many amps from our batteries, meaning they last longer. Now, that's a huge part of Electrathon because we're only given a certain amount of battery power, and so that is incredibly crucial. Another thing to account for in aerodynamics is drag. Now, drag is essentially a stopping force of our car due to imperfections in our aerodynamics, disruptions of airflow, basically slowing the car down. We can minimize this in a few ways, one of which is not using wings. So wings is typically how people generate downforce. Now, we're going to still use a front wing because it doesn't have a lot of drag, but we're going to eliminate the need for a rear wing by using ground effect and a diffuser. So we're going to go on and talk about how our front wing is going to help our car, our overbody aerodynamics, and ground effect. When talking about the aerodynamics of a car, one of the most important things is how that car initially enters the airstream. So ways to control that is through the use of a front nose and wing. Now, these really provide three key components. The first is, of course, to provide downforce. The second is to control how that air flows over the car. And the third is to use that air to help cool certain components of the car. Now, the first way, and the first thing that we have to talk about, is downforce. How exactly this wing creates downforce. Now, it acts in essentially the reverse of an airplane wing. So, due to the wing shape and the way it's sized, we're able to create an area of low pressure underneath the wing, which sucks the wing to the ground and the rest of the car with it. Now, this is essential to creating downforce because now this is going to suck the tires down and make sure our car handles properly. The next thing that this front nose and wing does is direct the air over the car. Now, the way it does this is through the use of wing elements right here. Now, again, using the same concept of having low pressure underneath there, these wing elements are able to create little vortexes that join together into big vortexes right here. Now, the use of these vortexes is to help move dirty air off the tires and around the car, because that dirty air would flow over the car in a bad way and make sure that our aerodynamics doesn't work how it's supposed to be. So by doing this, we're able to move that dirty air around our car and make sure that the rest of our car has undisturbed, nice, cool air. Now, the third thing that we're able to do is also use the front wing and nose cone to cool the car. Now, through the use of this vent right here, we're able to send nice, cool air back to our batteries and make sure they stay at a nice operating temperature so that the battery management system doesn't kick in and shut down our batteries. Now, one thing I haven't talked about is the wheel pods right here, and the hub covers. Now, what these are to do is to also help reduce drag and also move the dirty air away from the car. So these wheel pods aren't actually full-scale wheel pods. They don't cover the entire tire. They're just a thin strip of carbon fiber above, which helps push air off the top of the tire. Now, this is still effective, but it's not as effective as, of course, a wheel pod, but it also allows us to not use as much carbon fiber and to keep still the wheel nice and exposed and lightweight. So now I'm going to go into the underbody aerodynamics
basically ground effect in the diffuser, and essentially the science behind it and how it works and the evolution of it. So what ground effect is based upon is the Venturi effect. And so what this essentially is let's say right here we have a pipe. And in this pipe we're blasting air through it. So we have the same amount of air coming in as leaving, because that's how it's going to work. The flow is going to work that way because it's the exact same. It's constant. Now let's say down here we have a pipe, except for it's got a kink in the middle where it's a little bit smaller. We still have the same amount of air going in and going out. But because it's smaller here, the air has to move through faster. This creates an area of low pressure, which also generates downforce. This will essentially suck us to the ground without the hassle of overbody aerodynamics creating lots of drag. So now I'm going to be talking about the original version of ground effect, which was developed in the late 70s and early 80s and banned in, I believe it was 1983. Now, how these worked was, let's say this is the top view of the car. And the driver sits right here in the cockpit, the engine back there, wheels here, wing, whatever. Right here, these side pods, you have these Venturi tunnels, where this effect is taking place. So let's say this would be the road, and this is the underside of that tunnel. So you have the Venturi effect taking place. And then here you have these side skirts put along it between the wheels that was essentially sealing the air and make sure that you have this large area of low pressure sucking towards the ground. This increased lap times tremendously. It was a large amount of downforce in the corners and much higher cornering speeds. However, there was a drawback to this. Because this design was so reliant upon these side skirts, every time one of them broke and got to be taken out, you would lose an incredible amount of downforce in a corner. This was dangerous, and the FIA actually banned it due to this effect, and now we don't have ground effect. So I actually told a little bit of a lie. Ground effect actually will be used next year in F1 in 2021. Now, it is slightly different than 80s ground effect. And so you still have these side pods which have these Venturi tunnels through them. However, there's a slight difference in how it works. Now, they do have these Venturi tunnels, but these side skirts, which was a large problem back in the 80s, they're slightly different. Now, the problem was, every time there was a dip in a road or they got hit, the seal was broken and downforce was lost. Now, to combat that, they actually attached these side skirts to the uprights on the rear suspension and move it forward about half the car, to where the Venturi effect is really taking place. Now, due to this, it can move up and down to make sure nothing's taken out of it, and it also maintains a high level of downforce. We're going to be using this in our car, and since none of this is regulated or restricted by Electrathon USA, we're going to use this and enjoy the effects of it. Now, the actual bodywork of our car will be constructed of a foam core and carbon fiber hybrid. What this will be is the meat of it being the foam core sheet with 2 layers of carbon fiber on either side. This will be sealed with an epoxy resin. What this will allow for is for it to be really lightweight and yet still super strong. Using these methods, we'll be able to form our bodywork into complex shapes to create the curvatures that we need to transfer the air over our car properly. In areas such as back here and right here, this is super necessary to make sure that the air flows nicely around the car while still providing downforce. Now, like I was explaining earlier, the front wing is crucial in putting air over the rest of the car, as you can see right up here. The air flows up and over the front wing and around the turning vane to direct it around the cockpit of our car and throwing the dirty air off the back. Now, on the same thing that Zach could talk about the ground effect takes place underneath here, but he showcased it much better in his area. Over here is what I was talking about earlier with the 2 vortexes directing the dirty air off the tire and around the car. As you can see, it comes off the end plate and the inside of the wing to create these 2 vortexes and direct the rest of the dirty air around the rest of the car. Now, as for the rest of the car, it'll be covered with the same foam core and carbon fiber around the entire chassis to make sure that it's still sealed in and provides a smooth surface for the air to flow over.
Okay guys, so in this segment I'm going to be talking about the drivetrain of our vehicle as well as the electronic systems. So I'm going to start out in the classroom for a couple minutes and then I'm going to move back into the CAD model and talk about more in depth about specifically stuff about electronics, but also give you guys more visual and some stuff on the drivetrain. So first I'm going to start out, I'm just going to touch out on, in the CAD model you guys saw Zach and Chris go over suspension. Here happens to be some of the coiloaters that we'll be using. And then, so we'll move into brakes now. We're using 4 Wilwood calipers like this. So we'll have 4 calipers, and then we're doing 2 Wilwood master cylinders. We got 2 of these right here, both of these guys. And what these allow us to do is one will control the front and one will control the rear caliper brakes. And what this allows us to do is we can vary the pressure using something called brake bias to each caliper, allowing us to differentiate the ratio of our pressure between the front and rear. So for instance, I can have 60% of the pressure my foot puts on the pedal go to the front brakes and 40% go to the rears, or vice versa, or however I really decide to set it. And what this allows us to do is distribute our braking force in a way that would help slow the car down faster than it would if we just had the exact same amount of force going into each side. So now I'm going to be going into electronics. Just to give a fair warning, because this is kind of like our power plant, obviously, we're not going to be giving a ton of information on how it works. We're not going to be giving specific numbers exactly, but I will say some stuff like this motor right here is very similar to one of the options that we currently have for our motor design this year. It happens, when we're looking at it, happens to be a bit smaller. This is the one we ran originally during fall leadership of last year, and then during state leadership we ran another motor that we happened to have on hand that was of this style but a little bit smaller. So that is one of our motor options, as well as another one that we're looking at buying. But now we'll move into the CAD model and talk about our batteries and other electronic components in our system, as well as a little bit more on the drivetrain, specifically going over stuff like our sprag clutch differential.
Okay guys, now we're going to start talking about the electronic setup of our car. So just to give you some basic rundowns on how the electrical system is going to work, we're using a DC power system. So that means it's a direct current, which is different from AC currents, which you find in your house, and DCs in most electronics and stuff. And we'll be using DC power in this case. Now, most of the batteries that people buy, pretty much everybody uses 12-volt batteries in Electrathon, and the difference between these battery systems is because each cell is 12 volts, not everyone has a total voltage of 12 volts. Most people run 24 volts, where they take two 12-volt batteries and run them in series, which means they connect them like on the diagram that you see on your screen on the left, which means it's positive terminal to negative terminal on each battery, and that adds up the voltage. So instead of, let's say, 12 volts 5 amp hours, it's now 24 volts 5 amp hours if you were to connect two batteries in series. So that's one way you can connect it. Or if you wanted more amperage, because with more amp hours you can make the battery last for longer. So for instance, if I had the same two 12-volt 5 amp hour battery packs, I could connect them in series and get 24 volts 5 amp hours, or I could connect them in parallel, which means I go negative to negative, positive to positive, and I could get 12 volts 10 amp hours. You can see this happens to be part of one of the battery packs. We happen to be running 4 packs of 4 in a series and parallel combination. This happens to be half of one of those packs. You can see where the batteries will connect into these bus bars, which add the voltage in parallel. So in this case, these batteries are added in parallel, their voltage. So let's say, like I just used an example, they're two 12-volt 5 amp hour batteries. The output at these two terminals right here would be 12 volts 10 amp hours. And so going over to design, we have 16 total for these 4 packs of 4. You can see 12 of them are under here and the last 4 are over here. And using these combinations of series and parallel, you guys can add up the math. We get 48 volts, and then I don't know the head math because these aren't actually 5 amp hours battery packs, but we get a lot of amp hour, and so that allows us to run our motor at a high voltage with a lot of amp hours to last throughout the race, because basically, since we have 1 hour, we can limit the amount of amps that our motor controller gives to our controller to the exact amount. Since the unit is amp hours, and the race is only an hour long, we just limit it to however many amps are in any amp hours the pack has to give. So for instance, if the total pack amp hours, the pack had 50 amp hours, I would just tell the motor controller, hey, don't let the motor use more than 50 amps at once, because it can only afford to give out 50 amps per hour. And that would let us make sure that we last the entire race. So moving on from batteries, there's also on our steering wheel, we have a custom designed steering wheel, which we will have race diagnostics. So as we're in the race, we'll have a screen that will display things like the RPM that the motor is at, the voltage of our pack, how many amps we're using, along with other race diagnostic data. We're hoping to maybe even potentially get lap times in. depending on that. So you can see this is just the rough model for the steering wheel, which will be 3D printed with a cavity for all the electronics to go in, and then be carbon fiber wrapped as well, along with the motor controller, which will be mounted at the back of the seat in this area right about here, and that will be moving into the live axle and rear end section of this. So you guys saw in the real world earlier, I showed you guys one of the motor options we're using. This motor happens to be the other option that we'd be using. And so either way, whichever one we do choose to end up using, it would work the exact same. We would just change out this mounting plate we've designed up here. This one happens to be for this motor. We would just change it for the other. But after this, the system's the exact same moving into the drivetrain. So we would have a sprocket right here on either motor with a chain. You can happen to see, just because you want to make sure there's tension on the chain, you can see the slot here, which will allow for a chain sensing system that we would slide a bolt up with a roller wheel on it on the chain to keep it tension at all times on the wheel, and that chain also connects to this sprocket that is right here. This sprocket happens to be custom designed by us and is a split sprocket, which means if we decide, we can change the ratio at which the front gear is and the rear sprocket is. By doing this, you can change the RPM and torque that the rear wheels are receiving. So for instance, if we just had the same sprocket on both sides, it'd be a 1-to-1 gear ratio, meaning however much torque and the RPM that motor is rotating at is the exact same as it is in the rear, which isn't always good. For instance, this happens to be a very high RPM motor, but we need more torque and less speed, like top end speed. So we would gear it so there's a smaller gear up here than there is back here, like you see here, which there isn't a sprocket over here yet, but you can assume that the sprocket's going to be smaller than what we have designed up here. And by allowing us to do the split sprocket, it allows us to take it off the axle that we have without having to disassemble the entire rear end. We would just simply unbolt it from this hub that we have designed and swap out to whatever sprocket gear ratio we want. In addition to just the sprocket, this hub that it attaches to is not just a direct connection to the two axles that are on it's attached to. There's actually two sprag clutches in between, buried in this assembly, and what these sprag clutches do is they allow us to have a limited slip like differential, which means instead of the however much power it's being applied to this sprocket by the motor, it's not directly connected to, well, it is directly connected to the wheels, but it doesn't distribute the exact same amount of power to the wheels. For instance, when you turn, if I was turning right, the wheel that would be on the inside to the right would be moving less of a distance than the wheel on the left. And if you have what's called a live axle, which means the two sides are directly connected, it can affect your handling and cause you to spin out. All cars have some sort of differential. So this axle that you can see here that goes down the center is actually two separate sprockets. It's split in the center, in these sprag clutches that are attached to only allow them to turn one direction, which is the direction that the motor pulls. And that allows us to, for when you turn, to act as a limited slip differential and give us that good handling. Okay, moving out from there, you have two pillow block bearings which hold this whole assembly in place. And then we move to our brake rotors, which we custom designed and are going to machine soon. And you can see these are the wheel-wood calipers, just mocked up in CAD, that I showed you guys earlier. Moving out further, you can see we have a mount for the wheel-wood calipers, and then you can see this universal joint right here. Now, universal joint is what allows us, it's actually up on the exact same system, is up on our steering column. And what this allows us to do is, you can probably see it better here, is allow this shaft going in to rotate still, but be at an angle. So we have that, and these go in with the suspension and allow us to the suspension to be moving well along with the axle and still have power to the wheels, which goes out to the wheels that have yet to be mocked up here.
So I'm just going to give you a real quick rundown of a little bit of our fabrication process here, as we're still fabricating the frame at this moment. So the first step in doing all this is we go and track in CAD all of our measurements, our angles, and our cutting degrees. So the first step to doing this is bending all of our angles. Then we cut those down to size, get all the angles right. If we don't get the angles right, it's a huge issue. We've learned the hard way. As you can see, we have a lot of clamps. We clamp this to the table very slowly. It doesn't move. That is to get all the warping out. So it makes it easier on us. We are just starting to fill in with our welds. We're almost done actually. Just about to get started on the suspension. So this is almost as clean as you'll see it before we get paint on it.
Okay guys, now in this section I'll be talking you through the beginnings of some of the fabrication of one of the pieces of our car. So this happens to be one of the front uprights for the car, and so you can see it as here. It's where in the future the wheel will be attached to, but right now you can see it as the plate that all the suspension linkages connect to. So now in the real world, you guys can see we start out with this big 1/2-inch thick piece of plate, and we've got a plasma cut out each of the uprights. So we're starting with the first one here, and because this piece of plate is so thick, the plasma cutter leaves more of a jagged edge than it normally would. So then we have to grind down this jagged edge to get it more square to prep it to go into the milling machine. So now we're just grinding this down, and we're about to go to the milling machine, where we will be facing off that plate surface that just got ground, squaring it off to the rest of the plate more. So by doing this, we're just making it more square, so when we rotate that piece and in the mill and face the whole thing, it will be very square in the mill. So for those of you who don't know what a milling machine is, it's essentially like a very big hand drill that you can clamp your work in a vise and keep it very secure and tight there, and so you can then move it around very precisely using the handles, as you can see Zach doing here with the milling machine. And so after he does this, we now are going into face this whole plate, and so this plate it's going to be the final thickness of this plate is going to be 3/8 of an inch thick, and currently it's 1/2 an inch. So you can see we're taking off all that old like rusty looking metal, and you can see the shiny steel underneath, and so both sides of this will get that treatment, and so it will be all cut down to a big piece of billet, which will then be machined into the rest of the upright.
Thank you guys for coming to our technical session. We hope you guys learned something and can use this for yourselves.
And we hope we see you guys at the track at some time in the future.